Fellow Toastmasters, good evening. Today, I want to talk about a subject that's very exciting to me and something that's very relevant to my life as well, because after I graduate from Berkeley this May, I'm actually going to be working for Starlink, which is a SpaceX project, working on bringing new satellite internet connectivity around the world. So I want to start this by talking about why does this matter? Why are satellites a new form of technology we should care about, given that they're not new? We've had satellites for many decades now. But I want to make a distinction between geostationary satellites, or GEO satellites, or GEO satellites, and LEO satellites, or low Earth orbit satellites, which is what Starlink creates. If you've ever seen dishes on tops of rooftops in apartment buildings or your house, those dishes are connecting to satellite TV satellites in outer space. And these are all geo satellites. So they're thousands of kilometers away from the Earth's surface, and they're really only meant to beam data down to Earth for you to receive it and then stream it on your TV. Now, if you want to have high-speed internet for things like playing video games or streaming internet to watch movies or TV, or sorry, not TV, or YouTube videos, you need a lot more quick internet, like lower latency internet, and you need it to be able to be a two-way channel where you can talk to the satellite and have the satellite talk back to you. So to enable that, people like Starlink engineers have come up with low Earth orbit satellites, which are much closer to Earth, around a factor of 100 times closer than geostationary satellites, and this enables much lower latencies in the communication channels. There's two challenges that I want to talk about here. The first of which is that these satellites, because they're so much closer to Earth, are actually moving across the sky really quickly. So a typical LEO satellite might be moving across the sky at something like 27,000 miles an hour. So if you want to talk to the satellite from your house on Earth, where you're not moving at all, you need to be able to track that satellite as it's moving really quickly across the sky. The other thing I want to talk about is traditional economies of scale don't work yet for satellite internet. For example, today, if you look at remote regions where there's not much internet connectivity, it's really expensive to build traditional fiber or traditional methods of connectivity to those regions. Paying Xfinity or Dish to lay that kind of infrastructure would be really expensive. So LEO satellites can break these economies of scale and penetrate those markets where they can enable access to more people in these underdeveloped regions. But I think what's even cooler is that if you have access to the internet in these remote regions, you can enable things like agricultural connectivity, where you have farmers that are able to monitor crop health on these rural remote farms away from urban areas, or things like environmental monitoring of rainforest conditions where there might not be any internet terrestrially in that area. So with that, let me get started into talking about some of the exciting engineering that enables all of these satellites. The first one that I want to talk about is that for Starlink specifically, they want to target internet connectivity around the world. And so because these satellites are moving so quickly, you need a lot of them to be around the Earth, orbiting all the time, providing constant coverage in any region around the Earth. So for that reason, currently there's around 5,500 satellites orbiting the Earth, but the plan is to eventually have over 42,000 satellites all in low Earth orbit, providing basically universal coverage around the planet, except for a few remote locations like the North and South Pole, where there aren't that many people living in the first place. And this is an artist's rendering of what these satellites actually look like in the sky. This isn't a real picture on the right side, but people have actually been able to see these strings of Starlink satellites sort of lighting up the night sky as they reflect the sun's light back down to Earth. So one thing I want to talk about here, which is it's a problem that you may not think exists initially, which is that because these satellites are moving so quickly across the sky, like I said, the dish on Earth that's talking to it needs to be able to track its location very quickly and very precisely as it moves across the sky. So originally I was thinking, okay, why don't we just use motors to do this? We can just have a motor on the dish on Earth that moves the satellite dish at an angle to make it match the location of the satellite that's traveling up in space. Well, as it turns out, the satellites are moving so quickly that in order for a motor to track it that precisely would be very challenging. And moreover, it would have to do this constantly every minute of every day for years, which means the motors would get burnt out very quickly. So as an alternative to this, what engineers have come up with is something called beamforming technology, which has existed already. But in this specific application, the way Starlink works is on these satellite dishes on Earth, there's this massive printed circuit board, or PCB, that has all of these kinds of chips on it. But these beamforming chips are chips specially designed to steer this beam of information across the sky to track the satellite's position and allow you to communicate with it even as it's moving at 27,000 miles an hour. So I think this is really cool technology, and I'll give a very short explanation of how it works because it is very complicated, but I think a visual could help. So let's start by imagining that you're in a pond and you disturb the water at one location, creating this wavefront that's sort of propagating out in water. And if you create another disturbance at a different location, like the image on the top left shows, you have these two wavefronts that are kind of propagating simultaneously outward. And because they're angled in different directions, you have this uniformly formed wavefront in the middle that's kind of darkly shaded here, where those waves are actually adding together. And it's doing what's called constructive interference. So in that middle region, these waves are adding together and really channeling that energy forward in one direction. In the other areas outside of that central area, there's not much wave energy being sent because the waves are sort of canceling each other out, if that makes sense. So then let's look down at the top, at the bottom left, where you can see that if you have like two antenna elements, you can get this sort of somewhat wide main lobe where that constructive interference happens, and you get these kind of unwanted side lobes where you don't want to be sending any of that energy. It turns out that if you add more antenna elements, like if you go up to 4 elements, you can increase the directivity of that main lobe, meaning how focused is that main lobe on the target that you're actually trying to get to. And the other benefit is that the side lobes, which are the unwanted lobes, actually become smaller. So you're more precisely targeting the exact location that you want to target by increasing the number of antenna elements here. The reason I bring this up is because the Starlink system actually has 1,280 of these antenna elements for each of these dishes. So it's this sort of same idea of constructive interference on a much larger scale, which allows them to create this really narrowly focused beam talking from the dish on Earth all the way up to the satellite in space. And Elon Musk has termed this satellite Dishy, or actually Dishy McFlatface, but shortened to Dishy for the purposes of humoring Starlink customers. Now, one cool thing about Starlink too is that all I've described so far is the idea that Starlink satellites up in space can talk to you, one consumer on Earth. So you might have a satellite dish in your backyard that's talking to the satellite. Now, one expansion of this idea is that, let's say you live in Alaska or some really rural community where you have a lot of people in a clustered area, like a community in Fairbanks, Alaska. And a better solution for a situation like that is actually to build a community gateway. So Starlink has built these infrastructure facilities where you have many of these large antennas, like these domes shown on the left. And these community gateways are then talking to the satellite dishes. And then the people living in these cities are actually just getting direct wired internet from these community gateways. So this would be the same as you having like a cell tower a couple of miles from your home and having a wired connection between you and that cell tower or Wi-Fi tower or things like that. And this is actually really interesting because if you think about a situation like data centers, where companies that build data centers tend to build them in more remote locations where they have the resources and the land costs being low enough where they can build these data centers. And you want to be able to quickly get data from satellites, let's say, down to those data centers. So you can have community gateways near the data centers that are capturing this data and then sending it over a faster wired connection to the data center themselves. So this is like a cool expansion of the original Starlink idea that they've been working on. But the problem with this is that these are really expensive to build. Each community gateway is more than $1 million to construct. So if you're just a small residential community, it doesn't really make all that much sense. So here's a really cool advancement that Starlink has made to solve this problem: space lasers. And this sounds really sci-fi and really fictional, but I promise you it's real. And the way this works is that instead of having a lot of community gateways on Earth, where you might need a community gateway for every small community that wants to use Starlink internet, the alternative that Starlink has come up with is that you can actually have satellites talking to each other using interspace laser links. So they're essentially beaming data to each other in these really efficiently designed high-speed lasers that are actually beaming over 42 million gigabytes of data per day. To put that into perspective, that's 42 petabytes per day, and the total amount of video that's uploaded to YouTube every day is about 1/10 of that. So they're essentially beaming 10 times the daily YouTube content across these satellites. And this really facilitates, or rather, it removes the need for a lot of community gateways to be built on Earth, which reduces costs for consumers, but also it allows you to just have satellites that are replacing other ones if one fails. So let's say the satellite that's targeting your neighborhood fails, you can just have other satellites talk to each other and beam that internet down to you from another community gateway to bypass that issue. So this is a lot of information that I crammed into this presentation, but I think it's cool from an engineering standpoint what satellite internet can enable, but also it's cool from an economic standpoint of how you can disrupt traditional economic barriers in regions that don't have internet connectivity today, and maybe bring advanced connectivity to them and open up new markets for agriculture or environmental science or deep sea mining. I think the possibilities are really limitless, so I'm excited to see what happens.